Welcome. This is Ben Houston, and for the next hour or so, we're going to be talking about assessing the accuracy of data collected from a UAV, specifically for surveying and mapping purposes. This is a version of the same talk I recently gave at the 2019 New York State Association of Professional Land Surveyors Conference. And of course, the concepts and approaches really aren't specific to drones. They're applicable to all geospatial or mapping data. Traditional photogrammetry, airborne LiDAR, basically any data used for mapping purposes applies here. This is the outline of what we're going to go through. We're going to spend the first few minutes just framing the error discussion and talking about some general concepts. And then I'm going to walk you through something that we call the 5 principles, and spend probably the bulk of our time talking about the sources of error, and then talk a bit about the current standards and how to go about testing. Probably in the whole discussion about error specifically associated with UAV data, the testing is actually the easy part and doesn't take very long at all. And the important part is really understanding the causes of error and how to minimize them so that we can reduce them. So, what's the problem? We need to be able to answer some basic questions, right? Simple questions like, how accurate is the data? Or can you produce data to blank, a certain specific accuracy that we're looking for? So a couple basic kind of conceptual ideas is what we're doing with our UAV, right? We're collecting the data and we're going to post-process it so that we can generate specific deliverables. This is kind of another framework where we talk about what it is we're doing with the UAV, right? Probably 90% of what people do with their drones is monitoring. They're just taking pictures or taking video, and that's great. There's a lot of value there. But when we're talking about mapping or modeling, we're in a whole different arena in terms of data collection and data processing and data accuracy. So I just want to frame where our lanes are, and what we're talking about here is mapping. We're generating mapping products, which are surface models, planimetrics, and various analytics. When we move into the modeling world, into the 3D environment, that's a different ball of wax altogether. So here's an important concept that we talk about specifically with generating UAV data, and that's the data quality triangle. Drones are known for collecting really, really detailed information, really high resolution photos, really dense point clouds. And that's what we're talking about there is in the lower left-hand corner, precision, really detailed information. But the question is, can we place that data accurately in space? Can we make accurate measurements off of that data? And can we go back out and collect the same quality and the same accuracy over and over again? So the 3 things work together: precision, accuracy, and repeatability. So this is kind of the classic Accuracy 101 cartoon that we're talking about. And I just want to kind of reiterate that the drones can collect highly detailed and highly precise data, but not necessarily that accurate. So what we want to do is be able to take that precise detail and move it into the realm of being both precise and accurate at the same time. So here's an example from a real drone project. This was a construction project, a bunch of earth moving going on in the upper left off the screen. And so we did some testing in an area that we knew wasn't changing, right? So the red bar is along a contour, so that should be pretty flat, right? And you can see the variability in the photogrammetric derived point cloud there. The graticules on the bottom where the cross section is shown are a foot. So you have anywhere from a foot to 2 feet of variability there, although averaging about maybe a foot to 18 inches of variability within the point cloud. If we were to superimpose upon that airborne LiDAR data and the density of airborne LiDAR data, it might look something like this. So typical airborne LiDAR data from manned aircraft is not as dense, not as precise, but you can see there's also a lot less noise in there. So we're getting a ton of points from the UAV, and somewhere in the middle of that point cloud we know is the ground. Now, when we want to assess the accuracy of this, we have to generate a surface. We're not going to assess the accuracy of the point cloud directly. We're going to have to derive something that we can check against. So we derive a surface from that point cloud and then apply checkpoints that we'll go out and measure, ground survey checkpoints, and check the difference between them. So we might actually get something like that. And that's where we'll talk about the concept of average error versus root mean square error in a couple minutes. But that's the difference between accuracy and precision. And when we're talking about repeatability, we're talking about, can we go out the next day and what would it actually look like if we flew it again the exact same way the next day? And so here's real data flown the following day, and with the point cloud being slightly off again. So the difference between the two surfaces, between the two flights, is part of your error. That's part of your collection error. Let's take a little shift here. I want to give a shout out to my colleague in Iowa, Mike Tully, who's been instrumental at a company called Aerial Services Incorporated, and he and his team at Aerial Services were early adopters in the drone space, and he's been working really hard to try to help understand this accuracy issue as well. And we gave a joint presentation last year together, and Mike came up with this really neat concept called the 5 principles of remote sensing and mapping. And so I just want to walk you through the 5 principles right now and spend a little time talking about a couple of them. So principle number 1, positional accuracy is the final product of detailed planning and diligent work. It doesn't just happen. You don't just buy a really good piece of equipment and assume that it's going to create really accurate data for you. You have to do diligent planning and hard work to make that happen. Principle number 2, everything contains error. All measurements contain error. And we kind of forget about this. What we tend to do is make our measurements, if we can show that they're within the accuracy specification that we want, then we sort of forget about the error and we just move forward as if there's no error in our data because it meets the spec. And since it meets the spec, we can forget about the error. So we really can't do that, even though that's typically what we do in practice, because all the different components compound upon each other. And so it's important to understand that all measurements contain error, even the reference data that we compare against. So here's just a quick sidebar on error. We all understand the concept of vertical error, that we might measure a surface and have a plus or minus above or below that surface in which we're calling that our error. So that might look something like this, right? Where we have this bar where we don't really know where the surface is in between the 2 black lines. It's somewhere in there, and we're going to assume it's the white line based on our error bar. Now, if we have horizontal error, especially if we have areas of slope, we have to account for the fact that horizontal error can contribute to vertical error. So our horizontal error then may result in vertical error. So in some cases, if we can just minimize our horizontal error, we're also reducing our vertical error. So this is just a slide that sort of summarizes what I just said. And this is particularly important in the change detection environment, where we want to look at surfaces over time and see what's changing, right? And we can only detect change within the accuracy limits of the system that we're collecting. And I would say this is particularly important for those of you who are interested in things like stockpiles or earth moving, sand and gravel, and you want to look at changes over time. All right, So let's kind of take a quick pause on that and talk about that volumetric error. So if we're going to be measuring to a vertical accuracy of 1/10, what would that assumed volumetric error be over an entire acre? So 1 acre is 43,560 square feet. So that translates to about 161 cubic yards. So we can't really say, if we're measuring to a vertical accuracy of 1/10, we really can't say what the volume changes are inside of 161 cubic yards, because that's within our margin of error for volumetric calculations. What does that translate to in terms of actual loads? Well, that's anywhere from 11 to 16 dump truck loads worth of material over 1 acre. All right, back to the principles. So principle number 3, the entire system contributes to the positional error. We tend to focus so much on the sensor, that whether it's a camera or whether it's a LiDAR sensor, that the sensor has an accuracy spec, comes with the manufacturer. And so we focus on the manufacturer's specification and we say, oh, well, that's the accuracy. That's the error. That's only one component of it. Principle number 4, accuracy standards exist and are important. And we're going to talk about that a little bit later, and how we need to start getting our clients and our staff and ourselves to move away from talking in terms of the national map accuracy standards and talking instead in terms of more current relevant standards that apply to the data that we're generating. And the last principle is that you must test accuracy to know accuracy. So we're going to talk a little bit more later about methods for testing the accuracy of your drone. I can't tell you how many times I get a phone call, somebody's got some data and they're saying, can you tell me how accurate it is? Can you help me make a statement about how accurate this data is? So usually I put my hands up and I say, well, unless you want me to close my eyes and put the Ouija board over the data, we have to actually perform a test. All right, the 5 principles again. Accuracy requires planning and hard work. All measurements contain error. The entire system contributes to error. Standards exist, and you have to test your accuracy in order to be able to make any sort of definitive statement about it. All right, let's move on. Anybody know what this is? This is an error ellipsoid, right? So when we make positional measurements, regardless of how many decimal places that we use and what the precision is, there's always some vertical and horizontal error associated with that positional measurement. So we might report it as if it's the exact center where C, A, and B come together. But in fact, what we're really saying is the size of this egg or this ellipsoid. The point is in there somewhere. We don't really know where it is, but based on the accuracy specification, what we're talking about is the size of the egg. Coming back to our old graphic here, when we're talking about the precision of our drone data, that's this small red circle. But then if we want to talk about the accuracy of that same data, we're actually talking about this circle here, right? So that data might be really precise, but it's only as accurate as the larger red circle. All right, principle number 3. Let's take some time to walk through what this means for a typical drone system, right? In this case, I've got about, 7 different elements on here that contribute to the entire system, and this is by no means a completely exhaustive list, but we're going to step through these one at a time. All right, when we're talking about the total sum of all the error from all those different 7 things or more, right? We got to make sure that we understand that the sensor itself, as I talked about before, may only be contributing to some small aspect of that, or at least some percentage of that. And our entire error budget, which is represented by the red in the beaker here, has to be less than our required accuracy. So the required accuracy can't just be tied to the sensor. It has to be tied to the entire error budget of all of the sum of the expected errors. Right. So we've got a lot of different types of platforms, and the platforms have different stability, they operate at different speeds, and they have different onboard GPS quality. So the platform itself is going to help contribute to some of the error. Not only are we trying to make measurements from a sensor, but we're moving that sensor around on a airborne robot. And so that aspect in and of itself is contributing to part of our error budget. Right. Then we have the sensors. We talked about that a little bit, whether it's LiDAR sensors or infrared sensors or typical camera sensors. And these sensors, when we're talking about cameras, right, not all cameras are made equal. And so the sensor obviously contributes a specific amount to the error budget. When we're talking about cameras, one of the things we want to make sure we eliminate is the rolling shutter problem, right? Rolling shutters are really popular for video. They do a great job with high resolution HD video, but they really don't work well for mapping purposes. So what we want to do is make sure that we have a camera that has a mechanical shutter, and then in addition, we want to make sure that that camera has a fixed focal length on the lens, right? Cameras that zoom in and out and have optical zoom in and out are going to have too much float and movement there. We want to have a camera that doesn't have any zoom at all. Right, fixed focal length on the camera. Other issues, we talked a little bit about the quality of the platform GPS on our drone. A lot of drones that are in use right now use a cell phone grade GPS, and so upgrading that GPS can be an important part of improving your accuracy. And we have some issues related to the relationship between the GPS signal and knowing exactly when the photo frame is being taken. So getting exactly at the mid-exposure point. So if we know either at the beginning or at the end or through some sort of fuzzy range of when the photo is taken. Now, if the platform is moving all the time, right, we're interpolating where that shutter timing is. So getting exactly at the mid-exposure point can actually improve our accuracy significantly. And because these cameras are not completely tight, right, there's always some sort of float or movement within them. Right, having a camera calibration and repeating that camera calibration periodically gives us camera calibration coefficients that we can put into the post-processing software, and that can actually improve our accuracy as well. Now, in some cases, if we're using a lot of ground control, the number of iterations that the software uses to post-process a solution reduces the need for camera calibration. But if we want to use less and less ground control, the more and more important camera calibration becomes. And I'll give you an example of that later on. So here's a kind of a dorky graphic of a skewed looking area of interest that we want to map. So we want to make sure that on our flight planning that we have sufficient coverage on our flight planning. So we're going to have to push our boundaries out a little bit to make sure that we get sufficient overlap on our boundary edges. Right? In this case, this is what most people do. Right? They do their flight planning right up to the boundary edge. And what we really need to be doing is extending those flight lines beyond the boundary edge, because the turnaround area for the drone data collection is an area where the data is going to be of lower quality, right? And the post-process solution is not going to be as good there. So we want to buffer out from the AOI so we can chop the edge off and just get the good quality rows of flight line overlaps. If we don't do that, what we end up happening is we end up shrinking the area of high quality data so that we might have really accurate data inside the red box, but anything around that outer boundary or edge is going to be suspect, and we actually see a lot higher error on the outside portions of our areas of interest. So we got to make sure that, we do diligent and proper flight planning in order to reduce the contribution of error to the project just from flight planning in and of itself. So here's an example of what we really don't want to see. So this is right out of Pix4D, demonstrating the platform or the camera orientation during flight at each image frame. And so you notice that what we have here is probably a case of just flying too fast, where and without a gimbal. So in this case, the platform is oriented far off of nadir, and that's contributing to our error. So we want to get as close to nadir as possible. If you notice in this case, the camera orientation is off by as much as 2 entire image frames from being nadir to reduce error. So what you prefer to see is everything lining up, the calibrated position of the image and the calibrated position on the ground being directly or as close to directly over each other as possible. Let's talk a little bit about the differences between how we're going to control our site. The simplest and most common way is by the use of ground control points, or GCPs. One of the things that we found is that there's a lot of variability in where you place your GCPs and how many GCPs you have and the quality of the GCP-based solution. And we're finding better and better results using more and getting more consistent results when we talked about the data quality triangle, the combination of accuracy, precision, and reliability or repeatability. So we're finding a much more repeatable results using PPK and RTK. So let's talk about a little bit about each of those individually. This is not a class in GCP collection or in PPK or RTK technology, but just a brief overview of the different approaches. When using GCPs, GCPs control the accuracy of the final product. And typically 5 to 10 points is good. We found that more than that isn't always better. And that's been consistently found by a number of different vendors and a number of different studies. The GCP layout and the flight plan really should be done together. Wherever you can expect to have higher error resulting from your flight plan, you might want to add more control in that area, whether you have flight overlaps or areas where you're going to be landing and then taking off again and stitching together different flights. You might want to add GCPs in those areas. And then because most photogrammetric approaches don't see well in vegetated areas, you might want to augment a ground control plan in areas of low confidence where you're going to have obscurity by trees and vegetation. So this is actually one of Mike Tully's slides in illustrating the importance of a good ground control plan. And this slide I actually took from a presentation given by Wolpert at the EnergyIS conference last year, where they saw a really nice job of studying the relationship between GCPs and accuracy. And this is their headquarters. It's kind of a flat area, a building, parking lot. So they put a whole bunch of control on it, and then they would reduce or add control in different configurations in order to see how the control plan affected the accuracy of the data of the exact same flight. So these are their results. And if you notice, as you move across, right, if you have no control, and then you put control in the corners, and you have 5 GCPs, you have control in the corners and 1 in the center, you're slowly starting to get your error down into that 0.3 feet, right? Well, where we want to get to is, the holy grail here is 1/10 of a foot. And or at least under the 10 centimeter. The 10 centimeter accuracy class is what governs 1 foot contours. So that 0.3 feet is approaching that standard, right? So probably we're getting close to 1 foot contours there. So 7 GCPs, 9 GCPs, and 14 GCPs, you notice that by adding more across the bottom, we're not actually improving accuracy. In some cases, we're just introducing more error and more noise. So the sweet spot is somewhere around 7. So our general rule of thumb is between 5 and 10, depending on the size and complexity of your site. And our goal is to get a calculated RMSE of under 10 centimeters. So if we can get to 0.3 or below feet, right, we're good to go for 1 foot contours. And we'll talk a little bit about the relationship between those numbers in a minute. So there you go. All right. One of the problems with using the GCP approach is that you can't use it on every site or every project, right? You may not be able to get access to be able to put in. Either it's an active site or it's a remote site or it's a wetland or something. Plus, if it's a large site and you've got to do quite a few GCPs on a complex site, time is money. So then are you sending in some cases, a survey crew and a drone crew, or in some cases, the collection of the control is what governs the amount of time spent on site, right? The drone flight only takes a short amount of time, and then the rest of the day is spent going around actually measuring control points. So if you can reduce the amount of control points that you have on site, you can reduce the cost. And one of the things that we found is not only doing that, but using PPK and RTK technology, you can reduce the amount of control and improve the consistency and the accuracy of the data at the same time. Like I said, this is not a PPK RTK class, but the general concept here, right, is that you're going to need some sort of a base station and a rover, right? Your rover is your drone. The base station can be either your base station that you set up, or you can use a local CORS station, depending on how far away it is from your project site. The only real primary difference between these two is whether or not the rover has a real-time communication with the base, or whether it's just going to collect data on its own for post-processing. So the cheapest way to do it is the latter, right, with PPK, not having the real-time connection. And then if you have the technology and the budget to move into the RTK realm, then you've got real-time data processing and corrections back to your base. All right, when using either one of these approaches, but we're going to talk about PPK because that's what we've been using more often than not, right? The shutter timing, or that mid-exposure point, is extremely important for getting accurate geopositioning. The GPS quality and the integration with the electronics becomes critical, and the camera calibration becomes critical. It requires, some additional effort, some additional hardware and software and post-processing expertise, but the result is that you get better accuracy and you reduce the need for ground control. So you actually, overall, depending on how much work you're doing with your drone, you can actually reduce the cost and improve the accuracy by using PPK. But it's going to require an upfront investment in some equipment. So here's an example of one. These guys are great. They're out of Alabama. They're a U.S. firm, but it's an add-on package that you can attach to an existing drone. Now, some drones are actually coming with this technology already integrated, but here's a closer-up example. You can see the higher precision GPS in the cylinder on the top, which mounts on a platform, and you see the cabling that goes down underneath the main body of the drone that integrates with that mid-exposure point timing. So not only are you getting a higher precision GPS, but you're getting it synced to the mid-exposure point timing of the image. All right, let's shift gears a little bit and talk about targets. Believe it or not, the targets you use and how you use them can introduce error into your post-processing. So the method of integrating your targets into your control plan is a source of error. So we want to minimize that source of error. We no longer can be using spray can, X's on the ground, right? We have to be able to manage error in our targets sort of at the pixel level, right? Think in terms of pixels. So can you identify the measurement point within 1 pixel? And generally speaking, that's pretty hard to do. Even when you're getting down to 1-inch or 2-inch pixels, that can be pretty hard to do. So we're in most cases, we're talking about a 2x2 block or a 4 4 squares or 4 pixels, and saying that our measurement point is somewhere inside there, right? So we might have an incredibly precise measurement point, but if we can't locate it to within less than 2 pixels, right, that's a source of error for our post-processing. Here's some examples, right? We got a painted vanishing point chevron on the left, and here's some newer technology. Those of you who are familiar with it from Propeller, they are pitching these things called arrow points, which you can just throw out on the ground, and they have a vanishing point in the middle. They collect their own. They have their own GPS unit, so they collect their own position. You just lay them out there for the duration of your flight and pick them up when you're done. It's interesting technology of geobits, right? The idea being that kind of like a QR code, right? That you measure the measurement point on the geobit, and because it's got a unique pattern, right? The post-processing software can identify it and locate the measurement point without you having to manually click in the image and try to manually figure out where the measurement point is. So some interesting technology there for ground control. But the point is that your targets can introduce error into your project. Right? So here's an example of what comes out the other end, right? So there you see 2 targets, and there you see the actual measurement points plotted up on the targets. And these are 1-foot contours, so you can see we're about a foot off between the post-processed image and where the ground control points actually show up. I'm not going to talk a lot about post-processing, but just understand that, there is a lot that goes into it. There's a lot of parameter settings and a lot of things that you can manipulate in the post-processing. We got hundreds of images that are overlapping at as much as 90%, and we're doing some fairly complicated mathematical algorithms. So we just have to be careful that just buying a piece of software and going next, 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 finish, and taking the defaults may not be giving us the best answer at the end. So understanding those parameters and how you can manipulate those parameters to improve the quality of your data can actually help you reduce error in the process as well. So coming back around, we're talking about mapping products, right? Mapping products for planimetrics, mapping products for elevation models and contours, and mapping products for developing analytics like change detection or volumetrics. All right, let's shift gears a little bit now and talk about the standards, right? So what are the standards? We've got standards for horizontal accuracy, we've got standards for vertical accuracy, and we've got standards for how to assess accuracy. Here's kind of a general list, right? We've got standards being promulgated out by ASPRS, which is the American Society of Photogrammetry and Remote Sensing. We've got the feds at the U.S. Geological Survey, which have traditionally governed topographic mapping standards and planimetric and aerial photography mapping standards. We've got the National Digital Elevation Program and the National Map Accuracy Standards, and we may even have specific standards specified by our clients, right? So we've got a whole range of standards out there. We have to understand how do we pull from them as necessary and get them to reconcile each other so that we're talking consistently and correctly with our clients. So here it is. Here's our friend, the National Map Accuracy Standards, which came out in 1941 and have been state-of-the-art since they were last revised in June of 1947. If you look closely, you can actually see on the slide, item number 2 is the vertical accuracy paragraph, and this is where they start talking about, 10% of the elevations need to be, plus or minus a half a contour interval. So the National Map Accuracy Standards are universally understood by all subsequent standards to not be applicable to digital data. So fast forward to 1998, right? In 1998, we have the NSSDA being adopted by the Federal Geographic Data Committee, which is not a standard per se for collecting data, but it's a standard method of reporting data. So all of the subsequent standards refer back to this in terms of the statistics and how we report. So this is where we start to get things like the RMSE statistics and the 95% confidence interval, and the difference between testing data to meet a certain standard or producing data to meet a certain standard. While it hasn't been tested, it's been produced using the same methods, the same techniques, and the same processing as it was tested previously. So how does the NSSDA relate to the National Map Accuracy Standards from 1947? Right, so the 1947 standards are most definitely paper map standards, right? They're talking about paper maps produced at a certain scale, right? They're not appropriate for use for digital data where we can zoom in and out all day long to ridiculously high or ridiculously low scales. But the thing that came out of the National Map Accuracy Standards is the terminology, like 1 foot accuracy, 2 foot accuracy, that we still use today. So we still use the lexicon and we still use the language of the 1947 standards. So we just have to figure out a way to crosswalk those to the current standards. So fast forward to 1998, right? The NSSDA standards apply to all point, vector, or raster data. Right? They establish the requirement to compare against a reference. And the reference has to be at least 3 times more accurate than what we're trying to achieve. Right? That's an important requirement in terms of checking our reference data. We can't just measure data, check against it, and say they're equal, right? And it defines the statistics for the RMSE and the 95% accuracy rules. I'm not going to talk a lot about these slides, but just understand that there's formulas in there that allow you to crosswalk back and forth between the RMSE and the accuracy. You can refer back to these slides later if you need to reference that. There's another formula going from the contour interval to the RMSE standards and back and forth again. And this table is really where we get the relationship between the reference data that we're going to use to check and then the data that we're actually checking. Then fast forward to 2004, and we have the National Digital Elevation Program publishing out guidelines for digital elevation data. So this is prior to drones really being, coming to the fore, and this is really in response largely to the popularity and adoption of LiDAR data for topo mapping. So point cloud data nonetheless, but LiDAR data for topo mapping. And it's these standards, the NDEP standards, that help us establish the relationship between point spacing and the accuracy of the contours and the surface model that we're going to be able to generate. So here, in this case, we're showing a graphic of regularly spaced columns and rows. And whether we're talking about points, mass points of regularly spaced columns and rows, or we're talking about cells in a raster data set, it's the same thing, right? It's the same basic construct. And so the distance between the points or the size of the cells, it's the same thing. That's what governs, one of the aspects that governs statements that we can make about how accurate the surface model is, right? So the spacing between the points, or the nominal point spacing, has to be equal to or less than the DEM post spacing that we showed on the previous slide. The idea there is that in your point cloud, you want to be able to have at least one point in the box. So if we go back up and we look at these boxes here, if we're generating a point cloud randomly from a photogrammetric process or from LiDAR, we want to have at least one point in each box. So the spacing between the points needs to be smaller than the size of the boxes. That's what that means, really. That's what that gets us at. And And this establishes a relationship between the size of those boxes and the contour interval that we can produce. So a 1 meter post spacing DEM, right, or 1 meter resolution DEM is sufficient for generating 1 foot contours, 2 meters for 2 foot contours, etc. And so we have these relationships down below where we have a 0.7 meter nominal post spacing, which is a typical LiDAR spec now. And that translates to a point density of approximately 2 points per square meter. And those two things combined should allow us to generate a 1 meter DEM and have a reasonable expectation of having one measurement in each 1 meter cell. And if we do that, we can generate 1 foot contours. And that's what the QL2 or the USGS Quality Level 2 standard says. So important note here is that higher density data, just because you have more points, doesn't mean they're more accurate. So, and that's a common misnomer, is that more points are somehow going to result in more accurate data. So higher density data might still fail the accuracy test. And the converse of that is you can have fairly low density data where each point meets a fairly high accuracy test, but it's not dense enough to be able to generate a high resolution mapping product. All right. So regardless, we're taking these points, we're generating a surface model, and we're testing the accuracy against the surface model. So regardless of how many points go into that surface model, it's the surface model that matters when we're talking about accuracy. So in surface modeling, right, the point spacing and the point density, while they're different metrics, they're kind of interchangeable, whether we're talking about 1 meter post spacing or 2 points per square meter point density, right? They're interchangeable. But with this high resolution data we're getting, particularly now with drone data, it puts the idea of the traditional DTM generated from mass points and break lines completely on its head, right? We have so many points that we really don't need as many break lines. Few, if any, break lines are needed. We can model most everything just from the point cloud. In fact, instead of the old idea was that you had mass points that were distributed widely and you needed break lines to be able to identify detail in between the points. That was the purpose of the break lines, is to identify detail that was missing from the mass points because the mass points were too far apart. Now we have so many points that when we use break lines, we actually have to remove points from the surface model in order to enforce the break line in the surface model. So we put the break line in and then we remove points around it. So we're going the opposite direction now. We're thinning the point cloud down in order to create our surface model. We're removing points around the break line so that we can enforce break line edges around things like water bodies, retaining walls, or sharp breaks in terrain. So the old school technique of mass points and break lines is now completely reversed and flipped on its head. All right, let's talk now about the latest standard, right? The most recent standard to come out, which was published in November of 2014. So it's been out for almost a little over 4 years now. And that's the American Society of Photogrammetry and Remote Sensing, or the ASPRS, Positional Accuracy Standards for Digital Geospatial Data. And these standards govern all mapping data, point data, vector data, raster data, right? We're talking about imagery, we're talking about point clouds, elevation, so both horizontal and vertical. And they're easily, you can find them on the web easily, or you can go to our website and you can download them off our resources page. I'll give you the URL at the end, drainagemapping.com. But the point is that in the standards, in the appendices, they have some very useful tables that help us crosswalk between the legacy standards or the historic standards that we're used to and the new current standards. So in Appendix B, we've got horizontal accuracy classes for imagery, planimetric data, and then vertical accuracy for elevation data. if you haven't already, I'd encourage you to pause here and go to the website and download the ASPRS standards so that you can open up Appendix B and see what it is I'm talking about here in the tables. Because I'm going to walk you through the tables in some detail just so that you understand how they work. So what we have here is, this is table B6, which is the table that governs planimetric data. So when we're talking about planimetric data scales, this is the table we go to reference, can we use this imagery to generate planimetric data at this accuracy? Or vice versa, if I need to generate planimetric data at a certain accuracy, will the imagery that I'm generating support that, right? And so when we're talking about drones, I want you to look in the middle of the table here. We're talking about the approximate ground sample distance of the imagery, or the pixel size. Now, in a completely flat terrain, right, ground sample distance and pixel size are approximately the same thing. We're talking about the same thing. Now, where the terrain is much more extreme, obviously high ground, there's going to be a less area in each pixel than there is on low ground, right? As you get further away from the camera, you're going to have more and more area per pixel. So where they're talking about ground sample distance in this table, and I'm using the term pixel size, kind of assuming a small variation in terrain, fairly flat terrain. Right? So in general, drones are going to give us imagery that's down to anywhere from the 1 centimeter pixel size all the way up to, say, a couple inches, right? So that's where we're 1 centimeter. We're talking, 1.25 to 2. That's about the 1 inch, 1 inch arena, all the way up to about 4 to 6 inches. Once you get to about 4 to 6 inches or 15 centimeters, right, we're no longer in the realm of drones, and we're moving into the realm of traditional large area ortho collections. But you can see here, if we're collecting data that is about 1 inch pixels, right? That's about 2.5 centimeters, right? We see that depending on whether we can get within 1 pixel or 2 pixels, accuracy, we're talking about data on these top 2 rows here on the 2.5 or the 5.0 horizontal accuracy class. And if we slide on the far left, and if we slide to the far right, we can see what that scale translates to in the National Map Accuracy Standards for scale. All right, so if we're collecting data at 2-inch imagery with the drone, what's the range of horizontal accuracy that we can hope for, right? So if we assume our pixel size and our GSD are the same for generally flat terrain, right? The answer is between the 5 and the 10 centimeter horizontal accuracy class. So let's just look at how that works. So if we're 2-inch pixels, right, that's about 5 centimeter pixels. So we'd be here on the table. And that puts us in this range here. So if you look on the left-hand side, we're looking at between the 5 and 10 centimeter accuracy classes. So we need data. We need the data to test out to between 5 and 10 centimeter accuracy class. Right. The next question is, assuming the imagery tests do show that we've achieved 10 centimeter horizontal accuracy class, right? What scale planimetrics can we derive from that imagery? So at this point now, we've collected 2-inch imagery from our drone. We've done our accuracy test, and we've proven that it meets the 10 centimeter horizontal accuracy class, and we want to make a statement about planimetrics. So what scale planimetrics can we achieve using the imagery base? So we'll go back to the table in a sec, but the answer is 1 to 253 right off the table. We read that right off the table, which is approximately 1 inch equals 21 feet. For me, I'm a PE. That's close enough for me. I'll call it 1 to 20. I can put my stamp on that. I'm comfortable putting my professional stamp behind saying that's 20 scale. We can do 20 scale planimetrics. 1 equals 20 feet. So this is where we actually pull that from off of the table. So we have the 10 centimeter accuracy class on the left, which we've proven. We slide all the way over to the right, and we see that that's 1 to 253. So we do the math, 1 to 253, it's about 20 scale planimetrics. So if we need anything 20 scale planimetrics or below, like 40 scale, 80 scale, 100 scale, we're completely good to go with 2-inch imagery. All right. Now let's talk about vertical accuracy standards. So what I have highlighted in here, this is table B8 in the ASPRS standards. What I have highlighted here is the 10 centimeter line, which corresponds on the right-hand side of the table to approximately 1 foot. So this is where we get the relationship between quote-unquote 1 foot contours and the 10 centimeter vertical accuracy class. So if we want to be able to say that our elevation data is sufficient for producing 1 foot contours, we need to be able to meet or exceed the 10 centimeter accuracy class. That's what this table tells us. All right. There's a corresponding table, B9, which then helps us understand what the required point density is. Do we have enough points to be able to justify meeting the 10 centimeter vertical accuracy class? So if you see here in the far right 2 columns, we have the nominal point density, NPD, which is in this case pulses or points per square meter. And then we have on the far right column the NPS, or the nominal point spacing, which is the space between the points. So one is the density of the points within a square meter. The other is the spacing between the points. So what this table tells us is that we need to have at least 2 points per square meter, and that the maximum distance between those points really should be 0.7 meters, right? This comes from a typical airborne LiDAR spec, right? So if we're trying to achieve 1 foot contours with airborne LiDAR data, we need to have this point density. When we move into the drone environment, we're so much closer and we have so many more points that it just blows this standard completely out of the water. So we usually meet or exceed this by an order of magnitude or more with drone data. All right, so just using those 2 tables, let's just walk through this. So if we have the requirement for producing 6-inch contours, what's the minimum point spacing and point density that we can use? All right, we go to the table, we want 6-inch contours here. That means we're going to be in the 5 centimeter accuracy class. So that's from table B8. Then we switch over to table B9 at the 5 centimeter accuracy class. That brings us over to these 2 standards. So we need to have 8 points per square meter and a minimum point spacing or maximum point spacing between them of 0.35. So that's what we have to check on our drone data to make sure that we've met or exceeded 8 points per square meter and the recommended maximum point spacing. Like I said before, with most drone data, we typically exceed this by an order of magnitude. So usually the point density is not the problem with the drone. It's usually the accuracy, the actual accuracy. So that's where we get these numbers here, given the requirement for 6-inch contours, the minimum point spacing, and point density. Now, what's the vertical accuracy requirement for that data in feet? So we're talking about, again, 6-inch contours, and we're looking at our vertical accuracy requirement is 5 centimeters. So most surveyors typically don't think in terms of centimeters. So what's the translation of the 5 centimeter accuracy class in feet? We're talking about 1600ths, right? If we're trying to approach getting into the 10th, like if we can get to a 10th, we're golden, right? If we're just a little bit above a 10th, we're still good. If we're getting to 2/10ths, we're starting to move outside the realm of 6-inch contour accuracy. So we want to be under 2/10ths. All right. Now, the final question then, if we're going to create 6-inch contours, what's the minimum gridded point spacing for the DEM? Or if we're going to take that point cloud, remember that very first point cloud I showed you that was kind of had the thick band of points on it, right? If we're going to extract out a gridded column and row set of points to generate our TIN for our mass points and break lines, what's the point spacing required, minimum point spacing required for the elevation model in order to generate 6-inch contours. And that comes from our understanding from the NDEP, right? The NDEP standards. So if a 1 meter DEM is sufficient for 1 foot contours, then it goes to say that a 0.5 meter DEM would be sufficient for 0.5 foot contours. So that means that if we're going to generate mass points from our point cloud, we're going to extract out columns and rows of points to generate our surface model, right? Whether we're using a tin in AutoCAD Civil 3D or we're using a DEM in ArcGIS, regardless, we're going to make contours out of this data. So the minimum post spacing is 1.64 feet, right? Or basically 1.5 feet. So that's a number. We typically, when we're using drone data, we typically extract from the point cloud a surface model at a 1 foot post spacing. So that's where we use a rule, 1 foot post spacing. So if we use 1 foot post spacing, we know we're good to go in accordance with the NDEP standards for generating 6-inch contours. And it also just seems like a realistic number. And once you start getting smaller than a foot, you have so much noise still in the data. So it's a balance between trying to reduce the noise in the data to thin it out, but not thin it out too much that you exceed the standards for generating your contour intervals. All right, now let's shift gears a little bit. We talked a bit about the standards and how to apply the standards. Now we're going to talk about accuracy checking and accuracy assessment. So this graphic actually comes from a colleague of mine who's a surveyor and a photogrammetrist who now works at Wolpert, Mike Zoltek. And the story that Mike told me was to think of it like plumbing, right? So you've got your flight lines going back and forth, and those are like your pipes, right? So if all you did is go back and forth in a flight line, you'd get a lot of coverage, but the grid wouldn't be very tight, right? Those pipes would be kind of loosey-goosey and bendable, right? So in order to anchor them together, you got to do cross flights. You have to do cross flights, right? Which is like the solder anchoring the pipes together, right? That strengthens the mesh. And then in order to make them accurate, you got to bolt them to the ground, and that's what the control points do. The control points allow you to bolt them to the ground. So by having good flight lines with cross flights and control bolting it to the ground, you can generate